Welcome to this explainer on aircraft, ice, and rain protection systems. Today, we're diving straight into the fascinating engineering that keeps commercial flights safe from one of nature's most insidious threats. If you've ever looked out a plane window during a winter storm and wondered how the wings don't just freeze solid, you are in the exact right place.
Rain, snow, and ice are longtime enemies of transportation. That is a direct quote from our source material, and man, does it hit the nail on the head. When you're flying, visible moisture combined with freezing temperatures creates a literal life-or-death battle between machine and nature. It's wild to think about, but water droplets in the air can actually be super cool below freezing without turning into ice. But the split second an aircraft surface disturbs those droplets, they freeze instantly on impact.
To really understand how these automated defenses work, we're going to break this whole thing down into 4 quick steps: the enemy of flight, detecting the danger, anti-ice versus de-ice, and finally, wing and engine defenses.
Let's kick things off with Section 1, the enemy of flight.
So our source points out 2 main types of ice you might run into up there, and knowing the difference is crucial. First up is clear ice. This stuff forms from large droplets. Think big, puffy, cumuliform storm clouds, and it freezes gradually into this solid, heavy, smooth sheet that is notoriously tough to get rid of. Then you've got rime ice. This comes from smaller drops, like in flat clouds or light drizzle, and it freezes almost instantly. It creates this cloudy, mushroom-shaped buildup right on the leading edge of the plane.
What's really wild is the cascading effect this ice has on flight physics. It is essentially a devastating chain reaction. Once ice sticks, it completely ruins the smooth aerodynamic shape of the wing, which means your lift plummets. At the exact same time, drag shoots up, and the overall weight of the plane increases. Combine all that, and it forces the airplane to stall at speeds way higher than normal, which completely changes how pilots have to handle the aircraft during approach and landing.
But believe it or not, losing lift isn't even the absolute worst-case scenario. The ultimate nightmare is having structural ice snap off the wing during takeoff, just from the natural flexing of the plane, and getting sucked directly into the engines. Ingesting that ice can cause a catastrophic engine surge, intense vibrations, and literally a complete loss of thrust. Which brings us right into Section 2, detecting the danger. To stop that worst-case scenario from happening, the aircraft uses these little ice detector probes mounted right on the forward fuselage. Think of them as the airplane's nervous system for weather. They're wired straight into the onboard computers, constantly sensing the atmosphere outside to give the plane an early warning.
The way these probes actually detect ice is genius. They literally vibrate at a super high frequency, around 40,000 hertz. As ice builds up on the vibrating probe, the added weight physically slows that frequency down. The second the computer senses that drop in pitch, it fires up a heater inside the probe, melts the ice right off, and logs exactly 1 cycle.
Now, the magic number here is 10. The computers are always counting those heating and melting cycles. If that probe has to heat up and melt off ice 10 times, the logic kicks in, determines the plane is flying through severe icing conditions, and automatically triggers the aircraft's heavy-duty protection systems.
So what exactly are those protection systems? Let's look at Section 3, anti-ice versus de-ice.
The aviation industry generally splits its defenses into 2 camps. Think of anti-ice as a preventative shield. You turn it on before you hit the bad weather to keep ice from forming in the first place, usually by keeping the surface hot. De-ice, on the other hand, is more like a reactive sword. It's actually designed to let a thin layer of ice build up first, and then it actively breaks it apart and knocks it off.
And different parts of the plane need totally different defenses. For example, the wing's leading edge might use thermal pneumatic anti-ice, which is basically blasting hot air, or it might use pneumatic boots for de-icing. Propellers, they often use thermal electric systems. Windshields might use electric heat or even chemical fluids. The sheer variety of engineering solutions perfectly tailored to each specific component is just incredible.
All right, let's wrap this up with Section 4, wing and engine defenses.
To build that massive thermal shield we just talked about, large commercial jets actually steal incredibly hot pressurized air right out of the engine itself. This is called bleed air. They tap it off from a compressor port deep inside the engine, way before any fuel is even added, and then duct it through this massive network of pipes and valves directly to the front edges of the wings.
Once that pressurized hot air reaches the front of the wing, it gets pushed into a narrow passage and distributed through what engineers call
piccolo tubes. And yeah, they're called that because they literally look like the musical instrument, just a pipe with little holes drilled all along it. These tubes blast that superheated air directly against the inside skin of the wing, which completely melts any ice trying to stick to the outside.
And the sheer amount of thermal energy we're dealing with here is staggering. According to the source, the temperature switch limits inside the wing can hit a blistering 350 degrees Fahrenheit. If it gets any hotter than that, it triggers an over-temperature warning for the pilots. You literally have a flying furnace keeping those wings clean.
But here's the catch. There is a very strict order of operations. Because sucking ice into the engines is so catastrophic, the automated computer logic prioritizes the engines first. It will automatically fire up the engine anti-ice shield to protect the power plants before it even starts warming up those massive wing surfaces.
The real brains behind all of this is a system called ASIPS, or the Airfoil and Cow Ice Protection System, and it is incredibly smart. It uses a programmed 3-minute time delay. Why? Well, if you're flying through patchy clouds, hitting ice, then clear air, then ice again, you do not want those thermal valves slamming open and closed every 5 seconds. That would wear them out instantly. So the system holds the valves open for a solid 3 minutes just to make absolutely sure the plane is clear of the danger zone.
And the pilots aren't just crossing their fingers up there. The flight crew and the maintenance mechanics can actually watch all this invisible thermal warfare happening in real time. Right from the flight deck, they can pull up computer screens to check the air pressure, see exactly which valves are open, and monitor the hot airflow that's actively keeping their planes safe.
Ultimately, these hidden automated systems take what is genuinely a deadly atmospheric threat and turn it into a highly managed, routine engineering marvel. It really makes you appreciate the incredible science of flight. So next time you look out the window on a snowy winter flight, will you just see the wing? Or will you see the invisible, superheated thermal armor keeping you safely airborne? Thanks for joining me for this explainer, and keep learning.